To explore the universe, NASA is testing new technologies in a place you might not imagine. See how the sea provides an immersive environment to expand the limits of space exploration. Next on Real World. To get set for exploration of worlds beyond our own, NASA looks to places right here on Earth that mimic other places in the universe where we might explore. NASA calls these analog tests because these places are analogous to places like moons, other planets, and asteroids. You know when two things are analogous, they have a similar relationship. You've probably done word analogies in school. Things like Jupiter is to Titan as Earth is to, Luna, our moon. NASA looks for those same kinds of similar relationships when it does analog studies in Hawaii, where the volcanic soil is similar to the soil on the moon. NASA studies rovers and robots in the deserts of northern Arizona, where the landscape might be similar to what you would find on another planet, or perhaps even a big asteroid. And NASA studies the effects of gravity in Key Largo, Florida, below the surface of the Gulf of Mexico. We got some help from NASA engineer and special real-world correspondent Heather Paul, who had a fish-eyes view of the events in Key Largo.
Thanks, Josh. We're out here in the Florida Keys, and this is a really unlikely place. You don't think about this when you think about going to the moon or Mars. But in fact, NASA's doing underwater research right here. So let's go find out what we're doing.
This is the facility where the Aquarius habitat, which is the world's only undersea research habitat. It's about 5 miles offshore, and it's the closest thing to living in space that we could find anywhere.
Bill Todd is the mission manager for NASA's underwater research activities.
And what we do is we send crews to the habitat, astronaut and research crews. We send them to the habitat, and they go and live there to get a feeling of what it would be like to live in space.
The undersea environment simulates space exploration in several important ways. First, it provides an isolated, fully engaging setting, similar to what astronauts might encounter exploring other planets, moons, etc. In this environment, they can test various systems like communication and life support in a realistic setting. And it has a huge advantage over simulators.
We can do all types of things in simulators. In those simulations, we flip switches and we talk to the Mission Control Center and we go through a dress rehearsal. But at 5 o'clock we go home. The day is over and we go home and go back with our families and kind of wind down from all that. It doesn't really give you the sense, the feel for what it's like to live in an extreme environment. Here it's a lot different. You stay, you do your activities during the day, your EVAs, and then at 5 o'clock you're still right immersed, literally, in all of your activities, the life sciences that have to go on, the public outreach, and everything else that you have to do, which is similar to flying in space. This is the real deal. When we're doing missions and working here, and when we're in the habitat, that is a true extreme mission. There's consequences and risks to your actions, just like there is in space.
This underwater analog also allows engineers to test other systems. For instance, the backpacks that astronauts wear for EVAs, called the Portable Life Support System, or PLIS. It supplies oxygen, removes carbon dioxide, regulates temperature in the spacesuit, and contains communication hardware. By using a backpack rig to simulate the PLIS, the underwater environment allows engineers to figure out how best to configure this pack in different gravity settings, to make the astronauts as comfortable and productive as possible on each EVA. Here's Heather with Nick Skitlin, a project manager in NASA's Spacelife program.
For each dive, we'll take them down and then we'll put this backpack on, and we have them do a number of activities. We have them walk back and forth, we have them kneel and recover, we have them fall and recover, and by recover we mean just get back up. And then we have them pick up rocks and put them on a crate, and then at the end we have them climb a ladder and then come back down.
The exercise allows Nick and his team to adjust the backpack rig and find the most effective center of gravity to accomplish the tasks. Center of gravity is the point on which an object's weight is balanced. We use this same principle every day. Let's see how to calculate the center of gravity using a seesaw. The fulcrum is the point that supports the board for the seesaw. The weight must be evenly distributed on both sides of the fulcrum for the board to be balanced. But what would happen if a child who weighs 20 kilograms sits on one end of the board? and the second child, who weighs 25 kilograms, sits on the other end. The seesaw is no longer balanced. Math can help us solve this problem. Think of the fulcrum as the center of the equation. What's on one side of the equation must balance with the other side. Remember that our board is 5 meters in length. 5 meters is equal to 500 centimeters. The fulcrum is located at the center of the board, 250 centimeters from the end. If the child weighing 20 kilograms sits on a mark at the end of the board, she is 250 centimeters from the center. Where would the second child need to sit to balance the seesaw? We could write the equation to look like this. 20 times 250 equals 25 times what? By balancing the equation, we can determine the distance from the fulcrum that the second child must sit. The board will balance when the child weighing 25 kilograms sits 200 centimeters from the fulcrum. That's 50 centimeters from the end of the board. The team in Key Largo often uses this kind of mathematical reasoning to solve problems, like figuring out the center of gravity for many different kinds of exploration activities. Here's Nick and Heather with another example.
Actually, you have a backpack right there. Why don't you put your backpack on? Now imagine you were outside working and you had a shovel. And actually, pretend you're just like in your backyard and you're just shoveling some things up.
Can I be on the moon?
Well, not yet.
Oh, okay, all right.
Not yet. All right, so there you go. You're shoveling. All right, it's pretty easy, right?
Yeah.
Now
easy.
imagine somebody comes along and they put a jug of water in your backpack.
Okay.
And
Well, now it's getting kind of heavy, Nick.
right, it's getting kind of heavy. So now try it again.
Yeah, I think I'd probably have to change up how I would do the shoveling.
Right, and so that's changing your center of gravity. So we have the CG rig that allows us to change the center of gravity from being very, very backwards to very, very forwards to very high to very low and even to the side if we wanted to. And we can see how this affects the crew performance when they're doing a number of activities.
Once they figure out how to best configure the rig, they can take those lessons learned and apply them to actual portable life support systems that astronauts will use on EVAs. NASA has more analog tests planned throughout the year, including more work in Key Largo. You can follow the progress at www.nasa.gov.